Session 2, Computational Analytical Methods. What we're going to do today, as part of the review of calculus, is look at some practical uses of the differential calculus that we techniques that we looked at last week. Okay, so these will include determining rates of change, looking at velocity and acceleration problems, finding the turning points for a function and their nature, so minimum and maximum points of inflection, and practical problems involving minimum and maximum values. Yeah, so we'll spend this session having a look at some typical engineering problems, and may well be the type of question in many cases that you'll end up answering in at least the longer question part of the exam. So, rates of change. If a quantity y depends on and varies with another quantity x, then the rate of change of y with respect to x is the differential of that function, dy by dx. Other examples, if you've got looking at the rate of change of pressure in a tank, for instance, with respect to height, that would be dp by dh if p is pressure and h is height of the liquid in the tank. If you have a rate of change with respect to time, it's usually just called the rate of change, and you don't bother to add the with respect to time bit to it. Okay, that's just a convention. So for example, rate of change of current is di by dt, rate of change of temperature d theta by dt, and so on. So you tend to drop the with respect to when it's time. So in terms of looking at a problem, first problem of the week, the length L meters of a certain metal rod at temperature theta degrees C is given by the formula given there. I'm not going to read out all them numbers. Determine the rate of change of length in millimeters per degree C when the temperature is 100 degrees C and when the temperature is 400 degrees C. So what's the first thing we have to do to solve that problem? Yep, quite correct. Differentiate the given function and then substitute in the values, the two different values for theta, to get the rate of change for those temperatures. Okay, so have a go at that, and then for those watching the video, we'll put the solution up and then I'll run through it afterwards. So just to sum that up, we're looking at finding a rate of change. So we're going to, that's the function for the length at a given temperature in meters. So we find dl by d theta, where theta is the temperature in degrees C. So we differentiate to find that, and then we substitute in the values. So when the temperature is 100 degrees C, we substitute that value into the formula for the differential and get a result. First one being 0.13 millimeters per degree C. So this is the result in meters. Then we move the decimal place 3 places to the left to get it in, or take 3 off the index to get it into millimeters. And then when 400 degrees C, we get a faster rate of change of length of 0.37 millimeters per degree C. Yep. All happy with that? Have a go at the next one. Okay, where do we start with a solution to this? What do we have to do to use the product rule? What have you done, Lewis? So what did you let u equal then? T don't come out with it, does it? And is it 1.8? You didn't say minus. Is that what you got on you? Well, I think it's minus. Yeah. And dv by dt yeah, so they're the first steps in the process of using the product rule. Let u equal one of the functions, let v equal the other, and differentiate those two functions. So then we put that into the product rule to find ds by dt. So what's the first thing in product rule? V, so a sine is it u or is it v? Mind up. U according to your sheets I've given you. But with the product rule, it doesn't really matter which way round you put them. But if you get in that habit, it does matter with the quotient rule. You've got to get the right order for the denominator and the numerator. So we're talking 2 e to the minus 0.9t. I've got to multiply that by dv by dt, 10 pi cos 10 pi t, and add to that. So now it must be v sine 10 pi t times minus 1.8 e to the minus 0.9 t. Yeah. And then we've got to put in to that what we got to do with that now. We want to find, what's the question asking for? Find me. Determine the velocity of the end of the spring after 1 second. Yeah. So ds by dt is the velocity, Yeah, we're going to talk about that in a minute. Anyway, I'll put it down as ds by dt. So like a link into the next part is equal to 2e to the minus 0.9, t is 1, times 10 pi cos 10 pi plus sine 10 pi minus times minus 1.8 e to the minus 0.9. And if you plug that into your calculator, you should get 25.55 centimeters per second for the units. Because S, the displacement's in centimeters with respect to time. Nope. Look in your yeah, right, e to the ax, yeah, we got t instead of x here, so that don't come out, just the a comes out, just the constant in front. Yeah. Can get a little bit confusing when you're using a different variable to x, but we make a table with t and all the other things you might have the independent variable Louis. Alright? So all happy with that. Yeah? So we can use differentiation to find a rate of change of something that's the rate of change of a quantity that's changing. So the slope of a graph really is what this differentiation is all about, is finding the slope we can get. So, moving on to another topic of differentiation, and that is of problems involving velocity and acceleration, of which you've just done one really. Rate of change of in centimeters against time. You've found the velocity of that spring at a given time. So if we have a car, for instance, that moves a distance x meters in time t seconds along a straight road, if a velocity v is constant, then v is equal to the displacement divided by time in meters per second, i.e. it's the gradient of the distance time graph. Yeah. And the gradient, we all know that for a straight line, y is equal to m x plus c, c being the intercept, m being the gradient of that graph. And so if we differentiate velocity is the displacement or the rate of change of position of an object with respect to time. In this case, dx by dt. Okay. However, if velocity isn't constant, so we had a velocity graph, something like that, then the distance time graph is not a straight line. It might be that like that shown below, and that's something getting very fast, very quickly. Okay, never mind. In the previous slide, we saw that a slope of a distance time graph represents the velocity. So if we got this line AB, and that's a tangent to the curve at x, then the slope of the line AB is the velocity at that point. So if we differentiate and then find what the value of the differential is at point x, then we know what the velocity is at that point in time. So we can find the velocity of a displacement function by taking differentiating with respect to time. Okay. Secondly, acceleration. The acceleration A of a car is defined as the rate of change of velocity. How much faster is that car going every second? And so the slope of velocity time graph, as shown below, must represent acceleration. So if we differentiate a second time, or if we differentiate the velocity function, we end up with a function for acceleration. So if an expression for velocity is known in terms of time, then velocity can be found by differentiating that velocity expression. So to summarize that, acceleration A is dv by dt. However, v, so acceleration is the rate of change of velocity with time. V is dx by dt, the rate of change of position or displacement with time. Therefore, acceleration is given by the second differential coefficient of distance x with respect to time. So that's written d2x by dx squared. That means the second differential of x. To get from the function x to there, you differentiate twice. So the body moves a distance x meters in time t seconds, then distance equals that x equals that function at a given time. Yes, you spot a typo there, Seppi. You're right, that should be dt squared. Sorry. Well done. Spotted my deliberate mistake. Alright, it's a copy and paste mistake, I expect, and not remember to change it. Okay, so summarising, is given by the function you have in the first place. Velocity t is the gradient of the distance time graph, okay, and the acceleration a potential of the original function with x, we can say as 2x by dt squared, and I got it right that time. Alright? Velocity time. So the gradient of the velocity time graph is the acceleration. So we can have a whole host of different problems around acceleration and velocity of an object and use calculus to solve those problems. So let's have a look at one. The angular displacement theta, radians, of a flywheel varies with time t seconds and follows the equation 9t squared minus 2t cubed. So we've got this function. Theta 9t squared minus 2t cubed. Determine A, the angular velocity and acceleration of the flywheel at time t equals 1 second. And B, find the time when the angular acceleration is 0. So just before you start, what's the sequence of things you're going to go through to find those answers? Differentiate to find velocity. Yeah. Differentiate again to find acceleration. Yeah. and then substitute in 1 second. That'll do A. Work B. The time when the angular acceleration is 0. So you'll set second differential to equal 0 and rearrange for t. And for those watching the video, the answer will be on part 2.